structure of power system. The major components of power system: generating stations, transmission, sub-transmission and distribution system. Generating stations and a distribution system are connected to transmission lines, which also connect one power system to another. A distribution system connects all the loads in a particular area to the transmission lines. Now in generation, electric power is generated at a voltage of 11 to 25 kV, which then is stepped up to the transmission levels in the range of 66 to 400 kV. The first step down of voltage from the transmission level is at the bulk power substation, where the reduction is to a range of 33 to 132 kV. This step down is from the transmission and grid level to sub-transmission level. The next step down in voltage is at the distribution substation, normally two distribution voltage levels. First one, the primary or feeder voltage, that is 11 kV. Second, the secondary or consumer voltage, that is 415 volt 3 phase or 230 volt single phase. The distribution system fed from the distribution transformer stations supplies power to the domestic or industrial and commercial consumers. Now we will talk about the classical method and then gradually move. These are the subsystem of a power system and associated control. In transmission controls, reactive power and voltage control, HVDC transmission and associated controls, where generator power, tie flows and frequency, they need to be fed back to the generation controls, and it is the feedback signal, and then generation is being controlled. And similarly, we have the many generators simultaneously take control action. Now we are discussing power system operating states: normal state, alert state, emergency state, in extremis state and restorative state. Now in normal state, all the system variables are within the normal range. The system is able to withstand a contingency. Now in alert state, all the system variables are within the normal range, but the system is not able to withstand any contingency. Now preventive action will bring back the system to the normal state. In emergency state, system variables are not normal. Emergency control actions may bring the system back to the alert state. In extremis state, shutdown of a major portion of the system. Load shedding and control system separation are done to avoid a complete blackout. Now in restorative state, control actions are taken to restore the system. The system will go to alert or normal depending on the system condition. Let us talk about basic concepts and definition of power system stability. The stability of an interconnected power system means is the ability of power system is to return or regain to normal or stable operating conditions after having been subjected to some form of disturbance. Now the stability is a condition of equilibrium between opposing forces. Under steady state condition, there is equilibrium between the input mechanical torque and the output electrical torque, and the speed remains constant. If there is a perturbation, the equilibrium will be upset. Now the change in electrical torque of a synchronous machine following a perturbation can be resolved as follows. System stability can be broadly classified into rotor angle stability, voltage stability, and frequency stability. Each of these three stabilities can be further classified into large disturbance or small disturbance, short term or long term. Now the rotor angle stability. It is the ability of the system to remain in synchronism when subjected to a disturbance. Now, rotor angle stability is further classified into small disturbance angle stability and large disturbance angle stability. Now, let us talk about the small disturbance or small signal angle stability. It is the ability to maintain synchronism under small disturbance. Since disturbances are small, nonlinear differential equations can be linearized and it is easy to solve. So we can say it is the ability of the system to remain in synchronism when subjected to small disturbance. Small disturbance can be small load change like switching on or off of a small loads, line tripping, small generator tripping. We are discussing large disturbance or transient angle stability. It is the ability to maintain synchronism under large disturbance. Since disturbances are large, nonlinear differential equation cannot be linearized. It has to be solved numerically, but it is difficult. However, we can use a graphical approach called equal area criterion for analyzing the stability of a single machine connected to an infinite bus using the classical method. So, we can say it is the ability of the system to remain in synchronism when subjected to large disturbance. Large disturbance can be faults, switching on or off of large loads, large generator stripping. Now, the time domain of interest in case of large disturbance as well as small disturbance angle stability is anywhere between 0.1 to 10 seconds. And due to this reason, small and large disturbance angle stability are considered to be short-term phenomena. Next topic is power angle relationship.
Topic is power angle equation of a two-machine system. Now, real power is given by EG by X sin del. And this equation shows that the power transmitted from generator to motor varies with the sign of the displacement of angle delta between the two rotors. Now, this equation is called power angle equation. Now, power angle curve. If the curves delta versus P is plotted, then it is called the power angle curve. First, draw this picture. The maximum power occurs when delta equal to 90 degree. That means sin del equal to 1. So P max equal to EG EM by X. And this is the steady state stability limit. When the slope del P by del del is positive, then the system is stable. When the slope del P by del del is positive, that means minus 90 less equal to 90. It means that the increase in displacement angle result in an increase in the transmitted power, and so the system will be stable. And if del P by del del is negative, that it indicates that the system is unstable.
This is the rotor angle response to a transient disturbance. Case 1, it is a stable case. Case 2, it is an unstable case. This form is called as first swing, instability which is caused by insufficient synchronizing torque. Now the case 3, it is also unstable case. This form occurs when post-fall steady state condition is small signal unstable. Now in large power system, transient stability may not occur as first swing instability. And the time frame of interest in transient stability studies is usually limited to 3 to 5 seconds following the disturbance.
Swing equation. The behavior of a synchronous machine during transient period is described by the swing equation. Now the torque is given by T equal to I into alpha. So you can write I d2 theta by dt square. Now I is the moment of inertia kg meter square and alpha is the angular acceleration rad per second square. And where the theta is the angular position of the rotor in radians at any instant of time, but is the time in second. Now to measure the theta with respect to a reference axis, that is the rotating at the synchronous speed, we can write the theta equal to omega st plus delta, that is electrical radians. And where the delta is the angular displacement of rotor in electrical degrees from the synchronously rotating reference axis. And omega s is the synchronous speed in electrical radians. So you can write the theta equal to omega st plus del. Now differentiating with respect to t, we get d theta by dt equal to omega s plus d del by dt. Now differentiating once again with respect to t, we get d2 theta by dt square is equal to d2 del by dt square. Equation 5. Now the angular acceleration of rotor, that is alpha equal to, we write d2 theta by dt square. Is equal to d2 del by dt square. Electrical radians. We know that the synchronous generator, the accelerating torque TA is equal to the difference of input shaft torque, that is the Ti, and the output electromagnetic torque, that is the Tu. Equation 7. It is equal to d2 theta by dt square is equal to I d2 del by dt square. So we can write Ta equal to Ti minus Tu, that is I d2 del by dt square. Now multiplying both sides by angular velocity omega, we get omega Ta is equal to omega Ti minus omega Tu, that is equal to I omega d2 del by dt square. Equation 8. So you can write Pa is equal to Pi minus Pu is equal to Iw d2 del by dt square. Equation 9. Now Pa, Pi and Pu. Pa is the accelerating power and Pi is the mechanical power input and Pu is the electrical power output. So the angular momentum m, we can write is equal to I into omega. So we can write Pa equal to Pi minus Pu is equal to m d2 del by dt square, or Pa equal to m d2 del by dt square. This is the swing equation. Equation 10. It is a nonlinear differential equation of second order. Now let us come to figure swing curve. Unstable and this is stable. We know that the swing equation Pa equal to m d2 del by dt square. Now the solution of swing equation gives the variation of del in electrical radians with respect to time in seconds. Now the graph when plotted is called as a swing curve. It provides information regarding stability. Now if delta increases continuously with time, the system is unstable. While if delta start decreasing after reaching a maximum value, then the system will remain stable. To this topic, equal area criterion method applied to a machine swinging with respect to an infinite bus. The swing equation of a synchronous machine, we know that the m d2 del by dt square is equal to Pa. We can write Pi minus Pu. Or we can write d2 del by dt square equal to Pa by m. Multiplying both sides by 2 d del by dt. 2 Pa by m d del by dt, or d by dt, we can write d del by dt whole square is equal to 2 Pa by m d del by dt, or d del by dt 2 Pa by m d del. Upon integrating, we write integrate 2 Pa by m d del. We can write 2 by m root 2 by m integrate Pa d del. If d del by dt equal to omega, the velocity of the displacement angle with respect to the infinite bus. So you can write equal to d del by dt equal to root 2 by m integrate Pa d del. Now let us come to the figure. constant input line. Equal area criterion. Now under the steady operating, now for stability criterion, we can write integration pi d del into integration pu d del, or we can write area AFGDA is equal to area BCEDGFB. Now integration pi d del, we can write AFGDA. Now the integration pu d del, we can write BCEDGFB, or we can write area ABC plus area BCDGF. Now AFGDA, we can write this is equal to area ABC plus area BCDGF is equal to area BCEDGFB. We can write area CED plus area BCDGF. Area CED plus BCDGF, this is equal to BCEDGFB, or we can write area ABC is equal to area CED, or we can write this area denoted as A1 and this is A2, so we can write A1 equal to A2. Now the area A1 below PI line is equal to the area A2 above PI line. So this method is called equal area criterion. Now look at this figure. AB represents PI minus PU, that is the accelerating power corresponding to the initial angle del 0, and DE represent PU minus PI, that is the deaccelerating power, and when accelerating power is equal to the deaccelerating power, the machine tends to return to the original condition if there is balance between the two areas at del equal to del M. Now the system will remain in stable condition when A2 greater equal to A1. If accelerating area A1 is greater than the deaccelerating area A2, then the system will definitely become unstable. We can write PE equal to E V infinity xt dash plus xt sin del, or is equal to, we can write P max sin del. Now under steady state condition, Pm is equal to Pe is equal to, we can write P max sin del 0. Now sudden change in mechanical input come to this figure. Let's come to this figure. Sudden increase of mechanical input from PM0 to PM1. Now the operating point is shifted from A to B. Here PA equal to, we can write PM minus P, the accelerating power. Now the speed of the rotor omega increases above the synchronous speed, and the rotor angle and d del by dt also increased. Now at point B, del equal to del 1. That means PA equal to 0. But the rotor angle continues to accelerate due to inertia of the stored energy. Now the omega continues to be greater than omega s. Now at a point beyond B, say at the point C, all the stored energy in the rotor is exhausted, and the rotor speed starts reducing and deaccelerating at del equal to del 2, and the rotor starts deaccelerating. And at C, omega equal to omega s. Since the rotor is deaccelerating, the rotor angle begins to reduce. Now look at this figure. This is the oscillation of rotor. Now, this is for well-done system. The upward arrow in this figure represents d del by dt greater than 0. That is accelerating rotor. If this persists for more than 1 second, then the system might lose stability. But before 1 second or so, if it starts deaccelerating, that is the d del by dt less 0, marked by the downward arrow, then the system is stable. Now the rotor oscillates about the rotor angle del 1, the upper limit being del 2 and the lower limit del 0. So look at this previous picture. Upper limit del 2 and this is the lower limit del 0. Now for the steady state condition to be reached, the PM equal to P equal to, we know that the PM equal to PE equal to P max sin del 1. That means the accelerating area should be equal to the deaccelerating area. Now write the accelerating area. We can write A1 is equal to del 0 to del 1 Pm minus Pe d del. Just come to this picture. A1 integration Pm minus P del 0 to del 1 and A2 del 1 to del 2. So I can write decelerating area A2 is equal to del 1 to del 2 Pe minus Pm d del. Now del 2 we can write del max is equal to pi minus del 1. Just look at this picture. Del 2 is equal to del max, that is a pi minus del 1. So we can write pi minus sine inverse Pm1 by P max del 1 Pm1 by P max. Now del 2 is found out such that it is the maximum rotor angle beyond which the system goes out of control. Now come to the next topic. Sudden short circuit of one of the parallel lines. Just come to this figure. At point A, the short circuit fault is simulated corresponding to del equal to del 0. At point A, del equal to del 0. Now, due to this, the electrical power transferred is immediately brought to 0. That means Pe equal to 0. Now, at point B, at this point, Pe equal to 0, this point, and remains so till it is cleared at del equal to del Cr. Now, at point C, now the fault is cleared after time Tcr and corresponding angle del Cr. Now at point D, because of clearing of the fault by opening the shorted line and the heavy line transfer power, now P is increased to the point D. Now at point D, Now at point A, the rotor travels in the deaccelerating area till the point A. At A, the kinetic energy that is stored in the rotor is exhausted. Hence the rotor travels back to del CR and del 0. For steady state to be reached, these two areas, that means the accelerating area A1 and the deaccelerating area A2 should be equal. Now come to the next topic. To find the critical clearing time, that is TCR. Now from swing equation, we can write d2 del by dt square, that is equal to 1 by m Pm minus Pe, or d2 del by dt square is equal to 1 by m Pm. During fault, Pe equal to 0. Now integrating above equation, we get d del by dt, that is equal to 1 by m Pm t. Again integrating, we get del equal to 1 by 2m Pm t square plus del 0. This is equation 1. For critical clearing angle del CR, critical clearing angle del CR, time is TCR. We can write del CR equal to 1 by 2m Pm TCR plus del 0. This is equation 2.
Now we are discussing frequency stability. It refers to the ability of a power system to maintain steady frequency following a severe disturbance between generation and load. Now, during frequency excursions, the characteristic times of the process and the device that are activated will range from fraction of seconds like under frequency control to severe minutes corresponding to the response of the device, such as prime mover. And hence frequency stability may be short-term phenomena or long-term phenomena. Now let us talk about voltage stability. It is the ability of the system to maintain steady state voltage at all the system buses when subjected to a disturbance. If the disturbance is large, then it is called as large disturbance voltage stability. And if the disturbance is small, it is called as small disturbance voltage stability. Now in case voltage fluctuation occur due to first acting device like induction motor, power electronic drive, HVDC, then the time frame for understanding the stability is in the range of 10 to 20 seconds and hence can be treated as short-term phenomena.